Please find your seats. Good morning, everyone. Thanks for coming out today. So welcome to the public portion of Maria Drout's thesis defense. Before we hear from Maria about the exciting work that she's been doing over the last 5 years, I wanted to give you some background on Maria and share some personal thoughts. So Maria came to Harvard in 2011 after completing a bachelor's degree at the University of Iowa and a master's degree from University of Cambridge, where she did part 3 of the math tripos. And already as an undergrad, Maria has done quite a lot of research on in various areas. So she worked on topics related to the galactic center, to supernovae, in fact here as an REU student with Alicia Soderberg, and on the properties and variability of massive stars. So you can kind of start to see a thread developing in terms of her research. When Maria came to Harvard in 2011, she did a research exam work with Alicia and our PennSTARS group. And during that work, she discovered in PennSTARS data a new class of optical transients that she will tell you about today as part of her talk, and which is still not a fully understood class of objects. But it's not that often that somebody discovers a new class of supernovae, so that was a lot of fun. For a thesis, Maria decided to switch gears a little bit and kind of bring back her two passions, which are supernova explosions and the evolution of massive stars, and focus on type 2n supernovae. So these are supernovae that explode in a very dense environment and interact with a large amount of mass that was lost from the star before the explosion. So in studying these events and their environments, one can gain insight into both the final stages of evolution of very massive stars and then eventually how they die. And that will be the second part of Maria's talk today. Beyond research, Maria has also done some fabulous outreach work here at Harvard. So she was a founding member of Astrobytes and ComSciCon, the Communicating Science Conference, both of which I think have had quite an impact on the field. And so I think that's a great legacy that she's leaving behind. So that's kind of work and outreach. I would say that on a kind of more personal note, it's been a real great pleasure to have Maria in our research group. She's extremely knowledgeable about supernova explosions, about massive stars. In fact, I've learned a lot about massive stars from Maria. And she's been very generous in donating her time to help other students and other postdocs and been really kind of a productive member of the group. So she'll be missed. Okay, so she's done great stuff, and you might ask, okay, so what is Maria going to do next? So Maria received several prestigious postdoc fellowships, the Miller at Berkeley, the Einstein, the Carnegie Princeton. But she decided that those were kind of boring, so she ended up creating her own fellowship, which is a joint 5-year Carnegie Dunlop Institute with a 3-year Hubble at the beginning. So if you want to find out how to do that, you should talk to Maria. But without further ado, Maria, please tell us about supernovae.
Great. Thank you very much, Ido, for that introduction, and thank all of you for coming and being here today. So before I jump in too much into the thesis work that I'm going to share with you, there are, of course, many other people I have to thank. Grad school does not happen in a vacuum, and that's a good thing. So first off, I want to thank my advisor, Ido Berger, for the extreme level of support and freedom you've given me over the last several years as I've really tried to expand my research horizons. I also want to thank Cornelia Lang, Phil Massey, and Alicia Soderberg, all of whom have also served as research advisors and mentors to me over the years and whose support really helped get me to where I am today. I want to thank my committee, Bob Kirshner, Charlie Conway, Ramesh Narayan, and Roseanne Stefano. Hopefully I didn't burden you too much with the length of the thesis I gave you.
The first 300 pages were fascinating.
Yes, I apologize. I also really want to thank Enrico Ramirez-Ruiz, Avi Loeb, John Johnson, all of whom either wrote letters for me over the last year or just were there to provide advice and support throughout grad school. And of course, we all know that this place would not run nearly as well as it does without the great work that Peg, Rob, Nina, and Lisa do. So thank you all very much. Of course, there are many, many people in this building and elsewhere who have made the last 5 years exciting and fun. All of the people who have been in the research groups I've been in over the years, all of the other grad students who've sort of been there to cheer me up throughout definitely the last few months, and then all of my friends outside this building as well. Thank you all very much. And of course, I have to thank my parents, my family, my husband Mark, who's here today. Words can't really express how much I owe to all of you, and so I'm not actually even going to try, but just thank you very much. And then that leaves me with one final thank you, probably the biggest one of all, though, and that is my time machine hard drive. And this is going to serve as a public service announcement to all of you other younger grad students out there. Back up your computers. Because it happened to me, it can happen to you. Approximately 4 weeks ago, right before I was supposed to hand in my thesis, the hard drive on my laptop with my entire thesis, all of my data, everything crashed. It died. It was gone. So fortunately, I was well backed up, so you should be too. So with that, without further ado, I want to dive into the research. So very broadly speaking, the goals that motivate the research I do, if I had to pick one sentence, I would say it is to understand the evolution and death of massive stars and the origin of unusual astronomical transients. Now, this is very broad, but affects pretty much everyone in this room. And that's because massive stars, through their ionizing radiation, their stellar winds, nucleosynthesis, and their deaths as explosions, affect almost every other area of astrophysics, whether that be by synthesizing the heavy elements that are eventually necessary to form rocky planets, affecting the chemical and dynamical evolution of galaxies, or even just creating the neutron stars and black holes that are necessary for us to detect gravitational waves on Earth. Underlying all of these things and many others is our understanding of how massive stars evolve and die. So to that end, over the last 8 years or so, I've been involved in and undertaken a series of investigations both of supernova explosions and of resolved stellar populations in local galaxies, which can be used to test and as inputs of models of stellar evolution. So I'm hoping to touch on a little bit about resolved stellar populations in the conclusions part of this talk, but for the most part I'll be focusing on my thesis work where I've looked at the explosion properties, progenitors, and intrinsic rates of several classes of transients. So in particular, the title of my thesis and of this talk is Peculiar Transients as Probes of Stellar Evolution and Mass Loss. I chose this title for a couple of reasons. First off, I was sitting back and thinking that actually everything I have studied over the last few years could be considered odd in some way or another. Also, though, it was a question by one member of my thesis advisory committee who asked me, well, so you're interested in stellar evolution. What is studying all of these exotic things going to teach you about the general process? And I think that's a very good question. And as it turns out, after thinking about it, I do think it's important. And I'm hoping over the course of this talk to convince all of you at least a little bit of the same. So before I get into the results of my thesis, as a bit of introduction, I'm going to step you all through each aspect of this title to make sure we're all on the same page. So first off, transients. Time-varying astronomical sources. This can mean a lot of things. In this talk, I'm going to be focusing on luminous transients, so things which are most likely associated with the catastrophic death of some stellar system. So what about peculiar? Our good friends at Merriam-Webster tell us that peculiar means not usual or normal, whereas usual means what is done, found, or used most of the time. So this is not exactly a groundbreaking lesson in English for all of you, but the main thing I want you to take away and hold on to for the rest of this talk is that peculiar does not necessarily mean intrinsically rare. It simply has to be different from what we find most of the time. And in astronomy, when we look up at the sky, what we find most of the time is going to be related to, yes, what the universe actually produces, but also how we are looking. So as several people in the audience are keenly aware, every time domain survey that's ever been conducted has had to make decisions and compromises about its operating procedure based both on its technological capabilities and also its scientific goals. So as a brief example, let's say for some reason, I don't know why, you would want to find a bunch of type 1a supernovae. You could make the decision to point at this, return to the same section of the sky every single night. Then you'd have a beautiful light curve, cover a certain amount of area, detect a certain number of supernovae. Or you could use your knowledge about the timescale of this transient and instead only return to the same patch of the sky every 5 nights. Then your light curve would still be perfectly good for your purposes, but now you're covering 5 times the area, discover 5 times as many events, put them on a Hubble diagram, figure out that the expansion of the universe is accelerating, and win a Nobel Prize. So this would be a very effective use of your technological capabilities given your scientific goals. However, let's say instead in that survey this transient went off with a timescale an order of magnitude faster. Now with that design, you might get data like this. Or if it was cloudy on this night, you might get nothing at all. This transient would likely be considered peculiar to you based on the design of your survey. So fortunately for us, there have been, in recent years, a slew of technological advances, both in detector technology and computing power. We now have things like the Pan-STARRS 1 camera with 1.4 billion pixels, a 3-degree field of view. Between this survey and others, we're now able to survey vast portions of the sky on pretty much a nightly basis. This means that we're discovering a lot of things. This is a plot of just the number of supernovae detected as a function of time, and it's not even updated for the last few years. We are now detecting thousands and thousands of supernovae every single year, which is orders of magnitude more than just a few decades ago. This means that on one hand, we are now able to probe rare and exotic and intrinsically rare types of transients and explosions. But just as importantly, in my opinion, it means that we are now able to probe entirely new regimes of the time domain sky. We can have shorter cadences, which allows us to detect transients at shorter time scales and earlier epochs. Deeper images allow us to probe to higher redshifts. We can do untargeted surveys where we're pointing at random patches of the sky to discover explosions in a wide variety of host environments. At the same time, this has been coupled with advances in other wavelength regimes, so we're now able to study time domain and transient phenomena happening all across the electromagnetic spectrum. So all of this big influx of data has had a vast impact on the landscape of astronomical transients and supernovae. We've gone from this, which is what I consider the canonical picture of supernovae, at least from the time that I've been doing astronomy and in the field, as sort of the way that stars can die. So on one hand, you have type 1a supernovae, which are understood to be the thermonuclear disruption of a white dwarf. And then on the other hand, you have a couple different ways that massive stars can die. You have type 2 supernovae, which are the core collapse of massive stars that still have their hydrogen envelope intact when they explode, so typically red supergiants. And then you have type 1bc supernovae, which are the core collapse of massive stars who have had their hydrogen envelope removed, either via massive stellar winds or binary interactions before they explode as supernovae. So this is sort of a typical picture, and it's still a very good starting point as an understanding of how stars end their lives. However, with all of this new data, we're also finding many, many subtypes to each of these categories. We now have supernovae that have been able to start in one category, jump over into another, and we're discovering many types of transients that it's not clear how they fit into this classification scheme at all, and are likely from a wide variety of explosive processes. And it's this picture that people who study supernovae are trying to understand. So it's clearly a lot. I'm not going to explain all of this in my thesis, but it's within this framework that my thesis lies. If I had to give a sentence describing the scope of my thesis work, I would say that I have explored several of these new regimes of transient space which have been opened by modern wide-field time domain surveys to learn things about the final stages of stellar evolution and the physics of stellar explosions. So this is clearly a dense sentence, but it gets me naturally into the last portion of my title and of this introduction, namely, what can we learn about stellar evolution and mass loss from studying transients? And intrinsically, what that question is asking is what information is actually encoded in the light that we see from a given supernova or transient that goes off. And the picture is something like this. So every supernova we observe is going to be emitting light across the entire electromagnetic spectrum due to a wide variety of physical processes. So as observers, what we're typically trying to do is figure out, first and foremost, what is the emission process producing the light that we see? Based on that, what physical parameters does it depend on? And what from that can we infer about what exploded and how it exploded? So clearly, all of this is related back to stellar evolution in some way. For instance, if a given transient can launch a relativistic jet, it probably has something to do with the angular momentum in the core of the star and hence stellar evolution. But for this talk, I'm going to be focusing on two particular aspects of this. First is that encoded in the emission that we see from a given supernova is information on the final configuration of the progenitor explosion at the time of collapse. So what is the endpoint of stellar evolution? This is a prediction of models of stellar evolution that are dependent on all of the assumptions that go in before it. And in terms of transients, this can be simple. You can do things like by studying light curves and spectra, learn about the ejecta, how much total mass there is, what ions are present. But it can also be more subtle if you have very good data. So you can learn about things like the progenitor radius and envelope structure. This is because as a supernova blast wave goes out, it first has to blast through the envelope of the star. It will shock heat that star. And when that cools, it will produce emission, which if you can detect it, you can start to learn about these things as well. And second, encoded in the emission we see from a supernova is information on the pre-explosion mass loss of the progenitor system. And this is because similarly, as a supernova shock wave goes out, it is going to be impacting and interacting with the ambient medium surrounding the progenitor, which was shaped by the mass loss of the system. So by studying electromagnetic signatures of that interaction, we can learn about the density of the material and hence the mass loss the star was undergoing before it explodes. So for relatively low density environments, this interaction will show up mainly in the radio and X-ray. As you have a shock wave going out, you're going to amplify magnetic fields and accelerate particles, so you get things like synchrotron emission and inverse Compton. However, if you're exploding into a relatively dense environment, this can actually also start to impact the optical light you see from a given supernovae. So putting these together, you can see that the study of supernova really does offer us one of our only views of the final stages of stellar evolution, what stars are doing in the years and decades before they die. So putting it all together, what does studying all these new and peculiar types of transients teach us about stellar evolution? And these are kind of the three main points or summary thesis points that I'm trying to get at this talk. So it's a good time to pay attention and listen. I'm going to posit that by studying these new types of transients, we are increasing the types of progenitor systems which we can directly probe. We're also expanding our knowledge of what range of final configurations are possible for stellar systems, as well as learning new things about what type of physical behavior stars undergo and what type of mass loss they have in the years before they explode. So my plan for this talk is to take you on a bit of a whirlwind tour through three types of peculiar transients that I have studied during my thesis that I think exemplify each of these 3 points particularly well. Actually, it's why I chose those 3 points, but you know. So before I get into the results I'm going to show you, the data comes from a couple of main sources. First of which is the Pan-STARRS-1 Medium Deep Survey. So this was a transient survey run from 2009 to 2014. It had 10 fields that were scattered across the sky that we returned to on a nightly basis when they were in season. So it had a daily cadence, taking about 3 to 4 days to cycle through a set of colored filters. And during the course of the survey here at Harvard, we ran a difference imaging pipeline looking for transients in this survey. So this is just a schematic of the general process. During my thesis, I was one of the people who was partially responsible for keeping this pipeline going, as well as doing follow-up spectroscopic observations of any transients that we did discover. I think I calculated I spent something like 20 nights on a telescope doing follow-up for the Pan-STARRS-1 Medium Deep Survey during my thesis. So in addition to data and transients we discovered in that survey, I'm also going to be presenting results from a couple of detailed multi-wavelength, so radio to X-ray studies of nearby supernovae. So of course, this is a moment where I need to step back and again thank all of my scientific collaborators. During my thesis, I've learned a lot about how to undergo time domain observations, but any given transient only happens once. And so it really does take an army to coordinate all the different observations we obtain and to keep a survey running. So I have all of these people to really thank a lot for making the data I'm about to show you possible. So let's jump right in with rapidly evolving transients. So you can tell from the name, it's going to be fast, but get everyone on the same page, what I'm showing you here is a phase-space plot of supernovae. So on the vertical axis, you have the luminosity of the transient, and the horizontal axis is its characteristic timescale. In this case, how long it's above half of its peak luminosity. So for reference, this is where a typical type 1a supernova falls in this plot. Here's your typical hydrogen-poor core collapse supernovae. Your typical type 2 or hydrogen-rich event is pushed out to longer timescales, and it's this region here, events with characteristic timescales less than about 12 days or so, which is what I'm going to refer to when I say rapidly evolving. It's important to note that there's no actual gap separating these objects from the rest of the plot. It's simply objects with timescales short enough that it's telling you something interesting about the physics of the explosion. And to see that, let's review some of the main ways you get optical emission from supernovae. For type 1 or hydrogen-poor events, you're mainly going to be powered by the radioactive decay of nickel-56 synthesized in the explosion. For hydrogen-rich events, a lot of your emission will come from the recombination of the hydrogen envelope that was shock heated during the explosion. And then in several cases, you can have optical emission powered by circumstellar interaction. So the ejecta runs into a dense medium and you convert some of the kinetic energy of the explosion into optical light. So what you want to ask yourself is, in each of these cases, if you have a transient powered by this source, what are the physical implications if you have a very short time scale? For events powered by radioactive decay, your timescale is mainly set by the photon diffusion timescale. So in general, shorter timescales are going to mean smaller ejecta masses. Similarly, for hydrogen recombination, your timescale is going to be related to how much hydrogen is even around and able to recombine. And it's a little more complicated for circumstellar interaction, but your timescale is going to be related to what radii this material is located, as well as the density structure and things like that. But in each case, the main takeaway is that transients with short timescales are probing the extremes of both the configuration of the progenitor star, as well as the explosion parameters themselves. And to emphasize this more, I'm going to focus on start by focusing on one particular object which I studied during my thesis. This object here, this is supernova 2005 EK. This was an event that looked spectroscopically like a pretty standard type 1 supernovae. So there was no hydrogen there, but its spectra showed broad P Cygni features which are typical of a supernova explosion. But its light curve was very unusual. It is the colored circles here, and I'm showing you in several bands. It just plummeted. It decayed by something like 4 magnitudes in about 20 days. And when we model the light curve of this event, we find it is consistent with being powered by nickel-56 like normal supernovae, but you need a very small ejecta mass, only something like 0.3 solar masses of total ejecta. So this is incredibly small, and you have to ask yourself, how do you have an ejecta mass that small? So one way you can do that, if you want small ejecta masses, a good direction to go usually is to degenerate objects, things like white dwarfs and neutron stars, because there's just not very much mass around. So it's a natural way to get a low ejecta mass. And there are actually quite a few theoretical models out there for interesting things happening with degenerate objects, things like accretion-induced collapse, neutron star, binary mergers, helium shell detonations, that all predict fairly faint and rapidly evolving transients. And in particular, there's one class of models, a helium detonation on the surface of a white dwarf, that match our object particularly well. However, these models also give a very firm prediction that when you take a helium shell on a surface of a white dwarf and detonate it, you should end up with an ejecta that's dominated by elements like calcium, titanium, and unburnt helium. However, when we actually go through and model the spectra for 2005 EK, we find something very different. We find an ejecta that is dominated primarily by oxygen, and this is inconsistent with the nucleosynthesis you get from detonating a helium shell. So it's likely not that particular model, but instead the abundances we find are actually very consistent with what you get for other stripped envelope core collapse supernovae. So this may be an example of one of the most extreme stripped core collapse supernovae that's ever been observed. So the question then becomes again, how do you have the explosion of a massive star and only eject 0.3 solar masses of material? The first thing you know is that it needs to be a binary system. You cannot strip a massive star that much simply via stellar winds. But even in the typical picture of a binary progenitor supernovas, usually what you get is this. So you have a binary star. The primary will start to evolve, overfill its Roche lobe, mass transfer, and then explode. However, binary population synthesis models predict that in this scenario, you still, most of the time, will get at least a solar mass of ejecta from this supernovae. So we may be in a regime where you need to strip the star even more. So one possible way for this is you take a similar scenario, but now both of the stars you started with here are luminous or are large enough that they will eventually explode as supernovae. And then this evolution continues, and it gets pretty complicated, but the system keeps evolving, undergoes through several phases, probably goes through common evolution, which is scary because we can't model it very well, but then it'll keep going on, and eventually there might be another case of mass transfer, now from the secondary star onto its compact object companion, and then this star here will explode as a secondary supernova, leading to a compact object binary. And since our original work on this came out, there have now been quite a few theoretical models and papers coming out predicting that this secondary exploding leading to a compact object binary can produce ultra-strip supernovae, which are very similar to the object we see here. So these objects are important because every system, as you see here, it's labeled LIGO sources, all of the neutron star mergers that we detect with LIGO will have had to undergo a phase like this. And we may now be in a regime where we're starting to probe some of these explosions themselves. So that was one example, just to demonstrate the extreme nature of some of these things. But really, we want to move past individual objects. We want to understand the full range of types of explosions that happen on these short time scales. And more importantly, we really want to understand what their intrinsic rates are. Because knowing how many types of explosions occur at these short time scales can have implications for understanding of stellar evolution and what the final endpoints for stellar systems are. However, it turns out that this was pretty hard. Because if we go back to this plot, whereas all the other types of transients I showed you, I just picked representative examples to give you a sense of their timescales, until about 5 years ago, this was all that was known in this region of the parameter space, these 5 objects. And that's because of what I mentioned at the beginning of this talk, namely that until recently, many supernova surveys were optimized for type 1a supernovae and had fairly poor efficiencies at detecting transients at short timescales. So it's something that now, as our surveys are getting better, we can really start to address. And so that was our goal. What we did was we took the Pan-STARRS 1 medium deep survey, which remember I told you at the beginning had a daily cadence. It looked at the same patch of the sky every single night. And we did a systematic search within all 4.5 years of the data of the survey, looking for transients which occur at short timescales. And lo and behold, when you do this in a survey with short cadence, you find plenty of things. So here's just a montage of some of the light curves of the transients we found. We ended up detecting or confirming 10 new objects, the supernova luminosities in short timescales, which multiplied the number previously known by about a factor of 3. So this is what this region of phase space looked like before the survey we did, and this is now what it's starting to look like. So we're really starting to fill in this short region in the parameter space with new types of explosions. So what are these events? You can see right away if I go back. So for reference, this object here was 2005 EK, which I told you about already. So you can see right off the bat that many of the objects we're finding in pan-stars are significantly more luminous, up to a factor of 10 or even more in their peak luminosities. And this is actually pretty typical of the events that we found in pan-stars. So they are often quite luminous, have very blue colors, and have spectra that are actually dominated mainly by a blue continuum as opposed to standard supernova P Cygni features. And all of the properties are really consistent with just a hot, optically thick, expanding and cooling photosphere. And put all together, really the properties of these transients are much more consistent with being powered by something like shock breakout and interaction or recombination as opposed to by radioactive decay. And this has a few interesting implications for what the progenitors of these transients might then be. Some of them are actually luminous enough that you would almost need it to be the shock breakout from some sort of dense wind region around the progenitor star. Other ones could be shock breakout from a very extended or large progenitor. But in this case, you need there to be then no signature of sort of a normal supernova after the fact. There's no signature of that then. Or it's possible it could be some other sort of wind or outflow from a compact object or accretion disk. But all of these really are just adding on to have unusual implications for our understanding of how massive stars can die and what final configuration can have. There have been several theoretical models which have come out afterwards, some suggesting that things like failed or fallback supernovae could explain some of their properties. But it really is still very much an open question what these objects are, and it's something that we are working towards in the future, and I'll mention again at the end of this talk. But kind of one of the other, in addition to discovering a new type of transient with the Pan-STAR survey, the other thing that it allowed us to do, which is really very important, is it allowed us to calculate their rates. And that's because we selected these objects with a very stringent set of selection criteria, and we did it within the Pan-STAR survey, which we know exactly where Pan-STARs pointed every single night, what sensitivity it achieved on every night. So this allowed us to go through, and I did a Monte Carlo simulation where we injected thousands and millions of fake events into the Pan-STARS 1 pipeline, and to see really how many of them we were able to pull out again, to really figure out with what efficiency Pan-STARS was able to recover rapidly evolving transients. And this is what I'm showing you here. So this is redshift and efficiency on this axis. So the plots you should care about are the colored lines here, and then the black line here is for the entire survey. And this is the fraction of events that we injected in that we were able to recover. So even within Pan-STARS, we're only recovering about 10% of the objects, which is a little disingenuous because this is for the entire year. But even the in-season efficiencies for a given Pan-STARS 1 field, we're only peaking at about 25% at redshifts of 0.1 or so. So what we can do, though, is we can take these efficiency curves and invert them to figure out the intrinsic rates of these objects based on how many we did detect. When we do this, we find that the total rate of these luminous and blue transients that we found in Pan-STARS is something like 4 to 7% of the core collapse supernova rate. So that's not 30%, but that's also not 0.1%. This is a very real channel of transients that we need to understand what they are in order to have a complete picture of stellar death. So, summary for rapidly evolving transients. They're expanding the types of progenitor systems that we can probe. They're also increasing the range of final configurations we know are possible for massive stars. And the biggest takeaway from this section, if you remember one thing, is that they are not, in my mind, intrinsically rare. So that brings me to the second part of my talk. I'm going to briefly mention to you double-peaked supernovae. In particular, double-peaked stripped envelope core collapse supernovae. So that's a mouthful, so let's take a step back again. Stripped core collapse supernovae are the explosion of massive stars which have most of their hydrogen envelope removed by the time they die. As a result, most of their light curve is powered by the radioactive decay of nickel-56. This is especially true for the region I've highlighted here, which is incidentally where almost all of the data we've ever obtained on this class of objects falls. There's a lot you can learn from this part of the light curve. You can learn about ejecta masses, elements that are present, you can learn about asymmetries. There are many things that you can learn about the explosions. But as our supernova surveys are getting better and our cadences are getting shorter, we're also really starting to push to this portion of the light curve, the very early phases. And there are a number of other emission components which can contribute and even dominate at early times. These include things like cooling envelope emission, which I mentioned at the beginning. So this is when the supernova shock blasts through progenitor star. It will shock heat the envelope, and that cooling signature will be present potentially for a few days after the explosion, and what it looks like will depend on the progenitor radius and envelope structure. In particular, the bigger the star is, the brighter and longer lived this feature will be. But you can also have things like shock interaction with a binary companion or excesses of emission due to unusual outflows or ejections in the explosion itself. So this just shows you that if you can detect supernova early, and if you can detect additional components to the emission and actually disentangle them, they have the potential to serve as a very powerful probe for both the progenitor of the explosion as well as the explosion mechanism itself. So this is a very active area and really one of the frontiers in supernova research right now. There are a lot of groups actively pursuing this, trying to get very early observations. We've had several exciting results come out recently. For instance, there have been findings of excessive emission in type 1a supernova at earlier times that have been interpreted in terms of shock interaction with a binary companion and many others. I could give a whole talk on this, which I clearly don't have time for. So instead what I'm going to do is I'm going to focus on one particular object that I led a study of during my thesis, and then hopefully have a few minutes to tie it into a slightly bigger picture about what we're learning about supernova progenitors from taking very early data and coupling it with detailed multi-wavelength observations. So the object I want to spend just a couple of minutes on is supernova 2013 GE. This was an event that we got an extensive data set for, and really big tip of the hat to Daniele Saladic and Raffaele Margutti, who helped coordinate the follow-up for this event. So it was a type 1c supernovae, so hydrogen and helium poor. And really, from maximum light onward, there are several interesting things about it, but it really wouldn't have been flagged as peculiar, unusual at all if we had found it at maximum light. But it was not discovered at maximum light. It was discovered very early. And in particular, we have a set of very early spectra and UV observations that were triggered early on, probably within 2 to 4 days after the explosion itself. And these observations revealed several interesting things. First, there was an excess component of U-band and UV emission at early times. I'm showing you the U-band light curve here by itself and in comparison to other events. And this excess of blue light at early times, if we interpret it, the timescales and luminosities had never before been seen, and if we interpret it in terms of cooling envelope emissions, so such that it is probing the progenitor envelope structure, we require that the progenitor was extended, something like 30 to 50 solar radii or larger, which is significantly bigger than a typical Wolf-Rayet star, which is a hydrogen poor star that we know of that are more like 5 solar radii. And it also seems to be inconsistent with any hydrostatic envelope structure that's been computed for hydrogen-poor supernova progenitor to date. So one possibility is that several Wolf-Rayet stars have very massive winds. And so it's possible that the shock breakout actually occurred from within this wind region, so you're measuring a more extended wind instead. But we also obtained very deep radio and X-ray limits for this object, which put constraints on what the density of the medium around the star is, and constrained it to have a very low mass loss rate and density around the star. I'm just showing you the radio emission here. Ours is the stars compared to other type 1bc supernovae. So that may seem inconsistent with this idea from a shock breakout from a wind region. So we're still trying to piece together exactly what this means. One possibility, if this emission really is cooling envelope emission, is that the progenitor of 2013 GE underwent a change in its mass loss, potentially even ejecting a tiny portion of its envelope in the last 100 or so days before it exploded as a supernovae. And this may seem crazy, but there are actually some theoretical models out there which predict this now due to either instabilities or gravity waves that are induced during the final advanced nuclear burning stages in the cores of these stars. It actually predicts that some of that energy can be transported out and affect the mass loss of the star. So it's possible that we're now, as our data is getting better and better, starting to probe sort of how often and if this behavior starts to happen. So that was just one example of, as we're probing to earlier times, several things we can start to do with the data by having very early observations coupled with multi-wavelength observations. And you might say that, oh, well, 13G is just one object, it's very bizarre. And it's possible, that is definitely possible that that's true, but there are two things I want to mention with that. First is that if we had not had early spectra or very early UV observations, 13GE might not have been flagged as unusual at all. And so we really still don't have good constraints on how common this type of behavior is. It emphasizes that as our optical surveys get better and better, we also need UV observations to couple with it so we can have better constraints on this sort of behavior in the future. And in addition, I didn't have time to talk about it, but 13GE, if that interpretation is true, is really starting to fit into a broader picture. We're learning about the progenitors of stripped core collapse supernovae. It turns out that many different types of stripped core collapse supernovae show multiple emission components when you look closely enough. There's a class of partially stripped supernovae, so they have a little bit of hydrogen left, that show double-peaked light curves that have been known for a while, that implies their progenitors are very extended and potentially have unusual envelope structures. This has been seen in some long-duration gamma-ray burst supernovae as well, and the X-ray properties of these events show there might be an entire class of gamma-ray burst progenitors that have unusual envelope structures or mass loss regions around them. And so we really are starting to learn a lot about what the final structure of these stars are, as well as the diversity of pre-explosion mass loss and behavior they are undergoing. So that actually ties in very nicely to the last section of my talk, where I'm going to take this idea of enhanced or unusual pre-supernova mass loss and really push it to the extreme. We're going to talk about luminous and interacting transients. So there are a couple words you need to understand these events. First off, luminous. One of the other big discoveries of wide field time domain surveys in the last decade has been that there are several classes of supernovae. In this case, they are actually intrinsically rare, but several classes of supernovae that have luminosities that are 10 to 100 times that of a typical core collapse supernovae. These events up here in this regime are radiating on the order of 10 to the 51 ergs of energy, which is, for reference, what the typical kinetic energy of most supernovae is. So to power the light we see from these explosions, you either need a very energetic explosion or you need a very effective way of converting explosion energy into radiated light that we see. So as with all types of supernovae, you can subclassify these into several categories. The main classifications are hydrogen-poor superluminous supernovae and hydrogen-rich superluminous supernovae. And while the main source of the power of the intense luminosity we see from the hydrogen-poor superluminous supernovae is still very much debated, it's perhaps slightly less contentious for the hydrogen-rich events. And that's because many of them show these characteristic narrow hydrogen emission lines in their spectra, which are indicative of a supernova blast wave running into a very dense circumstellar medium, which is an effective way of converting explosion kinetic energy into radiated light. However, just because the source of some of the luminosity we see from these events is less contentious doesn't mean there aren't unanswered questions. In fact, these luminous and interacting transients are really just folding into a larger set of questions that was already raised by a broader class of transients in which these fall. And these are type 2n supernovae. So type 2n supernovae are this class of transients which show narrow hydrogen emission lines in their spectra. I'm showing you an example here. This class of transients is incredibly diverse. It spans a large range in peak luminosity, all the way from magnitudes minus 15 up to these luminous events I just mentioned with peak magnitudes around minus 21. They also have a wide variety of timescales from a few weeks up to several years. All put together, this broad class of transients composes about 7 to 9% of the core collapse supernova rate. And in all cases, these narrow hydrogen emission lines in their spectra are indicative of the supernova blast wave running into a fairly dense medium. And in this case, that shock interaction can convert some of the kinetic energy of the explosion into radiated light. So you can use observations of these transients, both their spectra and inferences from their bolometric light curves, to infer what the density of the material is around the progenitor. And when you do this, you infer pre-supernova mass loss rates, which range from 10 to the minus 3, 10 to the minus 4, all the way up to a solar mass per year in the years and decades before the explosion. So I'll pause for a minute because those numbers are crazy. To put it in perspective for people who don't want to study massive stars, what I'm showing you here is a plot of mass loss rate, solar mass per year, versus wind speed. So mass loss rate is getting bigger over here on the right-hand side. And these colored boxes show you the location of known and measured steady winds from evolved massive stars in local group galaxies. This is where they typically fall. So for reference, when we use radio and X-ray observations of other classes of supernovae to constrain their progenitor mass loss rates, these are the types of results you get. Typically, you are going to end up over on the left-hand side of this plot in the region of known types of winds that we've observed in massive stars. However, when you consider these type 2n supernovae, here's a smattering of just some of the constraints we get from these events. So some of the events do have inferred mass loss regions which are consistent with some very extreme winds from red supergiants that we've observed. But other events are really pushing out here in this region. And then especially when you consider the luminous events who have inferred pre-supernova mass loss rates of up to a solar mass per year, you're really clearly inconsistent with any steady wind we've ever observed. So especially when you consider the luminous interacting transients, it's very hard to escape the conclusion that some massive stars are undergoing intense, probably eruptive mass loss in the decades and years before they explode as supernovae. So this mass loss is not a priori predicted, and both the progenitor stars and the mechanism by which they lose this mass is uncertain. And really, this whole class of type 2n supernovae is folding in and emphasizing one of the biggest uncertainties that exists in our models of stellar evolution, and that's eruptive mass loss. There are examples of stars we know of that undergo eruptive mass loss. These are luminous blue variables, but those stars are not predicted in sort of the standard picture to explode as supernovae. In addition, eruptive mass loss is very difficult from a theoretical and modeling perspective, and it's not included from first principles in any of the models of stellar evolution that are widely used in the field today. So this really emphasizes how much we need observational constraints on what types of eruptive mass loss are happening and under what physical conditions that mass loss is happening. So in terms of intense pre-supernova mass loss, there are a couple observational constraints available to us. The first is we can use the transients themselves to understand the full range of CSM parameters that are found. So what radius is this material located at? What is its density profile? Are there multiple shells of material, all of which can give you clues as to what the source of this mass loss was? And second, we can study the progenitor stellar populations in which these explosions occur. So this can be their whole global host galaxy properties, where they're exploding within the light of their host in comparison to other transients, to try and get constraints on the physical conditions that are necessary for these explosions to occur. Both of these you would ideally like to have large samples of events to do in a statistical manner, and ideally you would also like to couple them together. And this is because type 2n supernovae, as I said, are very diverse. It's likely there are multiple types of progenitors hidden in the population, so you'd love to fold these components together to try and disentangle that. And this has been the broad goal of the last chunk of my thesis. I've been undertaking studies of both of these types using a sample of type 2n supernovae, mostly derived from the events we found in the Pan-STARRS-1 medium deep survey. So I'm showing you here a couple of views of the sample from the Pan-STARRS-1 survey. We confirmed 25 events throughout the year of this survey. So here they are in this phase space plot I showed you before, so time scale versus luminosity, and here are their bolometric light curves. You can see right off the bat there's a very large diversity in both their time scales and their peak luminosities. However, the Pan-STARRS-1 sample, Pan-STARRS is very effective at detecting luminous transients. As a result, our sample of type 2n supernovae is very heavily weighted toward the high end of this luminosity function. As a result, it really gives us leverage to understand these most intense types of mass loss. So I've been examining in both of these observational constraints above. For instance, and just to emphasize how intense these luminous interacting transients are, I want to point out some of these light curves here. Several of these events are emitting just as much light over a year post-explosion as a typical type 1a supernova does at its peak. So we can use these to try and understand the mass loss parameters found. For instance, if in order to reproduce some of these light curves with a shock breakout and interaction model, you require up to a solar mass of material and up to 10 per year at peak, and you need a dense shell of up to 10 solar masses to reproduce these luminosities at these very late time scales. In comparison, several of these lower luminosity events you can reproduce with a shock breakout with a more moderate pre-supernova mass loss rate and maybe only a few tenths of a solar mass of total material. With our sample, we've increased the number of luminous interacting transients with multi-band light curves available by roughly a factor of 2 from what's published in the literature now. And so we're really starting to probe things like the diversity of these transients. For instance, some of them you can see undergo very shallow, they take a long time to decay. Other ones reach similar peak luminosities. It's harder to see here, but then at late times they're maybe an order of magnitude fainter than others, which have implications for what types of mass loss environments you occur around these progenitors. So in addition to using them to learn about the CSM parameters, we really want to try and understand what progenitor stellar populations these events are occurring in. And like I said, the Pan-STARRS sample is very heavily weighted toward the high end of this luminosity function. And so where it really gives us leverage is to try and understand what the physical conditions required to produce these luminous and interacting transients are in comparison to both other interacting transients at lower luminosities and also other classes of energetic transients. So things like the hydrogen poor superluminous supernovae and long GRBs, and really try to understand how these energetic transients fit into this big overall picture in terms of their progenitors. So to do that, we've been going through and gathering information on the host galaxies, so it's got the images, spectra, where the supernova were occurring for both the Pan-STARRS sample as well as a much broader literature sample of luminous and other interacting transients. And I'm going to share with you some of the preliminary results from this work now. So first off, the host galaxies of luminous and interacting transients. There's one important piece of background that you need to understand some of these plots, and that is that it's been found that hydrogen-poor superluminous supernovae explode very preferentially in dwarf galaxies with low metallicity and high specific star formation rates. And I'm showing you that here. So what I'm showing you here is cumulative distributions of host galaxies. This is now host galaxy luminosity and host galaxy mass. The blue line is typical core collapse supernova hosts, and the black lines are hydrogen-poor superluminous supernovae. This is from the thesis of Ragnhild Lunin, who graduated last year. You can see that fully, especially when you consider the low redshift events, 80% of the superluminous type, so hydrogen-poor superluminous events, are occurring in galaxies that are fainter than the LMC. So this is a very strong environmental selection, and it's understood that this is telling us something important about the physical conditions that are necessary to produce the progenitors of these events, although it's still very much debated whether the key factor is metallicity, whether it's stellar mass, or something else. So when we look at luminous interacting transients, this is what we find. So we find that they are still offset potentially to slightly lower masses and brightnesses than other core collapse supernovae, but they are distinctly brighter and more massive host galaxies than the hydrogen-poor superluminous events. This is very statistically distinct. They are definitely not coming from the same types of environments exclusively as the hydrogen-poor superluminous events are. And of course, though, galaxy luminosity and mass is only one thing. We really want to understand the physical conditions in these galaxies. And it's been found that both hydrogen-poor superluminous events and long-duration gamma ray bursts prefer very low metallicity host environments. And I'm showing you this. This is a mass, stellar mass for the galaxy versus metallicity plot. So in green is superluminous type 1 host galaxies. In black, this is long-duration gamma ray bursts. And these contours represent typical SDSS star-forming galaxies. And you can see that these events are offset to very low masses and metallicities on average. When we look at our luminous and interacting transients and put our population on there, this is the type of thing we see. So there are definitely examples of galaxies that are still coming from these small dwarf galaxies with low metallicities. We also see another population that's up here in higher mass metallicity galaxies consistent with those found from SDSS. So it really seems like the physical conditions required for these events span a much broader range than what is required for other types of luminous and energetic transients. So another thing we can examine is where these events are exploding within the lights of their host galaxies. This has been used a lot in transient studies. So I'm showing you one plot here. This is cumulative fraction again versus normalized offset. So where is a given transient exploding with respect to the center of its galaxy normalized by the size of its galaxy? And one of the results that's been found in the literature is that standard type 2n supernovae, so not luminous ones, but just standard type 2n supernovae, explode in very similar environments to more typical type 2p supernovae, which is the explosion of red supergiants. And we find the same thing in our sample of events as shown here. And in particular, relatively few of them explode in the center regions of their galaxies. In contrast, type 1bc supernovae are more centrally concentrated in their hosts. So when we look at the luminous and interacting transients and put them on a similar plot, this is what we find. We find that they are much more centrally concentrated in their host galaxies, with fully 50% of the objects in our sample occurring with half an effective radius of the host galaxy. So for those who study supernovae, we find actually that the host environments for many of ours are similar to that of 2006 GY, which is perhaps one of the most canonical luminous interacting transients out there. It's exploded in the center region of an S0 galaxy. We find many additional objects, you can actually kind of see this, that are exploding in similar types of environments, the center regions of their galaxies, including the center regions of Milky Way and S0 type effects. Overall, we find that luminous type 2n supernovae are very heavily represented in the inner kiloparsec or so of their host galaxies, spanning a wide variety of types of host galaxies, but they're very well represented in the very inner regions of those. So that's perhaps indicating that something about the star formation that's happening in these regions is very effective at producing luminous type 2n progenitors, whether that be dense stellar star clusters. It could be some sort of dynamical or binary effect of the type of star clusters and star formation you get there, perhaps variations in the IMF. We're still working to piece this out together, but we're seeing a very strong effect and preference of this type. So I've just taken you on a very whirlwind tour, I'm sure, going through 3 different types of peculiar transients, which I've hoped demonstrated to you that by probing these new regimes of transient space, We're increasing the types of progenitor systems we can probe. We're learning a lot about the final configurations that stars have, as well as what types of intense mass loss stars undergo in the decades and years before they explode, and what physical conditions are necessary to produce those explosions. So I just want to take a couple minutes before we wind up talking about future directions, because I feel like this field is somewhere that's going a lot of places. Our surveys are only getting better. Newer and newer ones are turning on all the time. We are now surveying the entire sky almost on a nightly basis. So we're going to learn a lot about transients. At the same time, that's going to be coupled with increases in our theoretical capabilities, as well as with, and I think this is important and it ties it into my other forms of research, we're learning a lot now about the stellar populations in nearby galaxies. Multi-fiber spectrographs are allowing us to get spectra of many stars in nearby galaxies, and I think by really coupling all of these things together, we can make a lot of progress. So, in terms of the progenitor envelope structure I talk about, we're going to learn a lot from studying the transients in recent years, but we've also reached a point where we're learning that the progenitor envelopes of supernova progenitors in some cases are different from what we expect. So it almost gives us a chance to go back now and study the local stellar populations in local galaxies to try and understand this a bit. In particular, there's one class of supernovae that's been seen to explode as yellow supergiants, which is not predicted by many models of stellar evolution, but we're now at the point that in recent years we've gone through and gotten surveys of hundreds, almost thousands of yellow supergiants in nearby galaxies, and we can look at them and start to understand what their envelope structures actually are. And we're starting to see indications that some of the populations we see are actually consistent with these supernova progenitors we found. So we can now start to couple those together and study them from both sides. In terms of eruptive mass loss, this is another one where going forward, there's a lot we can do both from the supernova side and the massive star side. I shared with you some very brief preliminary results from my studies of the luminous type 2Ms from pan-stars, but there's a lot we can do going forward to actually incorporate not just effects from their luminosity, but also really quantitative estimates of their CSM parameters coupled with their explosion environments. And there's a lot we can do with that going forward, as well as with understanding what the CSM parameters for these events are at much larger physical scales. We're working on radio studies of these objects at very late time scales, which can actually help you probe the density of the material out orders of magnitude farther. You can also do this, again, from a perspective of massive star populations. As I said, we know that LBVs undergo eruptive mass loss, but it's a process that we still don't understand a lot about. And it turns out there are also, part of it is that there just aren't very many LBVs that we know about. But there are many objects we're discovering now that are considered LBV candidates with spectra similar to LBVs, but have not been seen to undergo outbursts. And so we're doing a lot to understand this population and how they relate to LBVs as a whole, and potentially increase our statistics on that phase of evolution by an order of magnitude or more. And finally, with the rapidly evolving transients, we've shown that there are many types of transients occurring in this region of phase space. And we really need to understand what they are to have a complete picture of the different ways that stars can end their lives. And part of the issue has really been this plot that I showed you here. Even pan-stars with its daily cadence was only reaching 10 to 25% in-season efficiency at detecting these events. So it's something that as we move forward and our surveys get better, we can optimize our surveys even more to really get better efficiencies at pulling out transients at these short timescales. And it's something, there are several things coming online in recent years, which you can ask me about if you want to, that are going to be much better at this. And hopefully, in particular, much better at finding them at short timescales so we can really start to disentangle what these objects are. For most of the objects in pan-stars, we only really constrain their evolution over maybe 20 to 30 days or so. So by finding more events nearby, we'll really be able to probe what they're doing at shorter timescales, as well as other wavelengths, and can hopefully constrain what their progenitors actually are. So with that, I will conclude and say thank you.
Time for questions. If we can turn on the lights. All right, let's at least raise it. So natural. Questions from Maria.
So, Maria, that efficiency thing.
Yeah.
I find that surprising. If you're looking daily, how can you miss 3/4 of the events, especially at low redshifts?
Yeah, so there's a couple things tied into that. First is that Pan-STARRS itself, it's looking every night, but it's doing so, it looks in G and R one night, then I, then Z. G and R, then I, then Z. So it's not a daily cadence in each band. And when I calculate those efficiencies, I used the exact criteria that I also used to select the sample of rapidly evolving bands. So when I looked through and searched Pan-STARRS, I had a very specific set of criteria required to select these, and those efficiencies are calculated using that same thing. And so it required that there were 3 points in 2 different photometric bands. Anyway, because the fact that it was cycling through the bands as opposed to doing every single night, coupled with my selection criteria, that really hurt it if then you had, because the other big thing that really affected the efficiency, especially when tied together with how it was doing it with the bands, is that if you lost any night due to weather, pretty much any night, and especially 2 nights in a row due to weather, you just kill that entire region. So one of the big issues moving forward with doing better at these is trying to minimize those effects. And unfortunately, to minimize weather, kind of the only way to do that is to start with, there are actually ways to do that. You can minimize weather. For instance, there are a couple of different supernova surveys that are coming online that are actually using multiple different sites. So there's something called KMTNet in particular, which has several telescopes coming online. So there's one in Chile, one in Australia, and one in South Africa. So if they're all working, you get a much better cadence. But then even if you have poor weather at one site, you still get something for each night. And almost to really do well at these short time zones, you might need to move in that direction, because otherwise it's just very hard to account for weather.
But could you do better with this data, with just changing your criteria? Just redoing the search in a different way?
I mean, it depends what you mean by do better.
Find more.
I could probably find more, but the data would be worse. So basically the cuts I had were so that we'd have enough data to say anything about the explosion at all. I didn't just want one point that was high and then limits that are low, because it's very hard to say something based on that. So I selected the criteria so that we would find objects that actually allow us to say something about the explosion. So we could probably find a couple more events in the data that, but I'm not sure how much it would actually show you.
So when you were doing these efficiency calculations, were you actually working with the image data or the photometry pipeline?
No, I was not working with the imaging data. I was working with the outputs of, and actually I was mostly working with outputs of what the noise even is that was achieved in each of the different images. So you sort of take a given transient, you move it to a random redshift, pick a luminosity from your luminosity function, and figure out what the light curve looks like, and then basically put it onto the information about when Pan-STARRS observed where, and then information on what noise was achieved on every given epoch. So you can also do it where you're actually injecting it into the images themselves, but that was not what I did when I calculated these efficiencies.
Could you tell us something about future surveys? I'm thinking about the Zwicky transient factor, which is optimized for rapid cadence and is always white light, so you don't have the photometry problem.
You don't get any photometry.
No, yeah, so the Zwicky transient facility, which should be coming online next year based out of Caltech, should be very good for this. They have such a big field of view, and they are optimized so they can survey pretty much the entire visible sky a couple times a night if they wanted to. The biggest things there, so they should find many of these events. The biggest thing there is they are still focusing, I think their intention now is still to focus on a single photometric band. So mainly R band, because the camera is so big, it takes them a very long time to change filters. And so every time they want to change a filter, it really affects how much they can survey. So they should find a lot of these transients, but it'll be mainly light curves in a single photometric band, which especially for these objects in Pan-STARRS, which we found are incredibly blue, it might be harder to disentangle some things. But no, they should definitely find many of these. As I mentioned, there's something called KMTNet coming online with multiple sites, which should be good at that. There's something called Black Gem, which is being built. Actually, the intention for it is to do follow-up to gravitational wave sources, but they're intending to do surveys of the night sky in very short timescales. So there are several, that's several years away still, but there are several things coming online in the next few years, which should be good at this.
What is the mystery about
the giant mass loss rates in these LBVs, I'm thinking of the classic example, Eta Carina, which must have lost something like 5, maybe even 10 solar masses.
Yeah, no, it's an example.
It happened, you know, it was in 1842.
Yeah.
So what is the mystery about its future?
What is the mystery? Yeah, so what is going
It's going to explode. I think you said it wasn't clear that these events would lead to superluminous supernovae, but how can it avoid it?
Yeah, so I mean, the biggest.
You got it right before.
No, I agree, and this is exactly right. So many of these superluminous supernovae, what you infer for the mass loss around them is very similar to what we see in Eta Car in terms of densities and total mass there. It's got a mass of like 10 solar masses right around it. I think the biggest reason why LBVs are not predicted to explode is that it's supposed to be a short transitionary phase, and so they're in many models of single stellar evolution, but again, those models don't include eruptive mass loss a priori, so it's very difficult, but they're predicted that they should then evolve over to the Wolf-Rayet phase and basically spend long enough there that the mass will still be there, but it'll be further out, so you're not running into it right away. But no, I agree. It's things like Eta Car that we're looking at here and maybe probing from the supernova side. Eta Car is also a binary, hence it's likely not a single star, so single star models are not ideal for that. Yeah.
So when you listed upcoming facilities, you very explicitly did not mention LSST. So the cadence is too poor, like if you change the cadence, would it be good?
Yeah, so clearly LSST will be good for this as well. But yeah, the biggest thing is the cadence, which is still being developed. The optimal plan for LSST right now is actually to do something similar to what Pan-STARRS is. So it will find many more than what Pan-STARRS did, but in terms of the quality of data or the redshift, it should be good because there should still be many objects, but the cadence is not ideal for these events. But if they do a sub-survey within it, which I know they're considering as options that has a slightly different cadence, it will also be very good at these, yes.
Going back to the eruptive mass loss, one of the direct observations of eruptive mass loss in normal type 2N supernovae is this precursor activity seen in 2009 IP and may be seen in a variety of others, though the data are still scanned. You're now looking at luminous type 2Ns. I wonder if the Pan-STARRS data was good enough to pick anything out.
So yeah, we did go and look at this to see whether there was any evidence for pre-explosion outbursts in any of ours, and we don't explicitly see anything, but it's unclear how constraining the limits are, because Pan-STARRS does find things, but because many of the events Pan-STARRS finds are at moderate redshift, so redshift to 0.2 to 0.3 is where most of our events are, even limits of like 23 to 24th magnitude in terms of overall luminosity, the precursors aren't that constraining. A few of our objects do show sort of variations and undulations in their light curves, one of which actually has a very similar time scale to that 40 days you see in 2009 IP as well. But yeah, we don't see anything in the years before the explosion, but it's unclear how constraining that is in sort of terms of the total output. Yeah.
So you showed that eruptive mass loss at a level that hasn't been seen before can be happening in these massive stars. At what level do you think that's going to affect stellar population models and the interpretation of spectra and observations of other galaxies, or is it occurring over too short a time scale to really have an effect when integrated over full lives of the population?
I mean, yeah, that's a very interesting question. In terms of the most extreme cases of these mass loss, the rates of these events, they are pretty rare types of explosions, maybe 0.1% of the core cloud supernova rate, but the eruptive mass loss in general, this is a large issue that if this is happening a lot, and our stellar models of stellar evolution aren't including it, it can definitely affect what we're inferring from galaxies, although I would almost say a combination of eruptive mass loss and just frankly the influence of binaries on populations, which will definitely affect the ionizing radiation from those stellar population synthesis models. Like, yeah, this will definitely affect things mostly.
Okay, thank you, Maria, for an excellent talk.
Oh, thank you.
For the fun part.
Yeah, right?
So it's 10:35. Should we convene at 11?
Yeah, do you think that's good, or do you think people would want to? Is that fine, or, I mean, I'm happy to start whenever.
Would it be 105? Would it be 105?
I think 106. Yeah.
That's what I was saying, that was a really excellent talk.
Thank you.